You are now highly familiar with orthogonal matrices. You learned about them in the chapters on vectors. You learned about them in chapter 11, definitely the last chapter. Okay, I forget the chapter numbers, but I've mentioned and introduced you to orthogonal matrices several times. Let's just say that. And one of the important properties of a orthogonal matrix is that they can rotate but do not scale a vector. In other words, the magnitude of UW is the same as the magnitude W for any vector W as long as U is a orthogonal matrix or pure rotation matrix. Now, if U comes from the SVD, if this is a left singular vectors matrix, then yeah, this property holds. So what you want to do in this exercise here, exercise 3, is first prove this fact on a piece of paper with a pencil. I actually did it in code, but the proof is pretty short and easy. And here's a little tip. I actually went through this proof already a couple chapters ago. So it's good to refresh your memory here. And then demonstrate this empirically by computing a singular vectors matrix from the SVD of a random matrix and create W to be just some random vector. So, how to prove this equality? The proof is pretty simple. You just want to write out, here we can square it. You just want to write this out as vector notation. So, the magnitude or the magnitude squared of UV, remembering that U is a matrix, but UW, sorry, I said V, but UW is still a vector. Okay, so the magnitude of UW is UW transpose times UW. And when we apply the transpose operation to this matrix vector product, of course, we apply the live evil rule, and that gives us W transpose U transpose times U transpose W. And here the idea is that instead of thinking about these two matrices paired and these two matrices paired, you think about U transpose U like this. And then, of course, this is the identity matrix. And so that gives us W transpose W, which is the magnitude of W squared. All right, so that is the proof in theory. Let's see it in demonstration. Here I'm creating a U matrix, and now, I don't care about either of these two outputs, and I don't really care about the input. So I'm just providing just some bunch of random numbers, right? And then here W is also random. Everything is random here, except the laws of linear algebra. Okay, now, because these are random numbers, we have no idea what to expect for the norm, right? I have no idea what this number is going to be. But the important thing is that the norm of U times W is the same as the norm of W. So this is the proof in theory, and here you see the proof in practice. We can run this again multiple times. Of course, the number is going to be different every time. But what's important is that the number is the same in both of these cases, so that's a nice empirical demonstration.